After. Okay.
I send a message to Melissa.
Okay. Okay.
Right.
How are you?
Wow.
You look like you're hangover.
Yeah. Mm,
Partying, huh?
no. Ah, no, no, no.
No,
No
just
party.
working.
Yeah.
No, I
Like,
see.
I was at a session just before. Right now, they came pricey. And then just after, I have to do my uh, ambassador duty
Oh God, a lot of
by
things.
running a session in French for base. Um,
I see.
and after
You
that,
look like you look so tired. I'm sorry.
I'm
You
tired.
should
I'm
listen.
really
You should sleep just a bit. Oh,
tired.
Melissa is here.
In fact, like, um, is more about dealing with all the things, not only just session. Like session is just like 10% of my time.
Hello.
The rest is all about logistic
Hello,
and stuff.
guys.
I mean, it's yeah. So all right. I think I will let you the lead. uh,
I
yeah.
know we don't have a lot of people here, but I believe they're gonna watch it because this is not
Yeah.
the usual day for them. But thank you
Okay.
for this session, Melissa. Seriously, we
Yeah,
really appreciate
ask
it.
they ask for the recording because in fact, yeah, a couple of them can't attend as it's Friday, etc. So yeah. All right.
Okay. Yeah, it's a pity. Maybe we can wait for a couple of more minutes for everyone else to join. I want this
Let me
session.
remind them also.
Yeah. We have this, so the session will be remarkable, right? Yeah. Let's let's try it with remarkable because of the calculations and everything that we have. So, yep. I'm not in Milan anymore, so I have this equipment with me now.
Yes, your background seems more gray right now.
Yes.
You were living in Serbia, right?
Yeah, for most of the time now. Yeah.
But I see you travel a lot, so it's really hard to keep up. Where are you?
Nobody knows.
Maybe just 1 minute too, so then we can
Mhm.
start. Mhm. Um, yeah. Are you traveling for the Connect, Melissa? Or are
Yes.
you planning to like
No,
um,
it's all the time. It's something, right?
oh, it's when I was like 20, I wanted to be a digital nomad, but now I realize I need some, home
Yes.
environment for me. It's really hard for me. I tried a bit to travel through the event. Right now I just say no because it's too I get too tired, I think. So I appreciate whenever I see people just travel all over the world.
Don't be a devil then.
I see
But I
noted.
believe it's like different, right? Because you're traveling for job, like, hey, I have Eat Global next week, for example. But it's not like, okay, I'm living right now in Milan and I want to go Mexico City next month, or I want to go to Buenos Aires in 2 weeks, or things like that. You have a place to crash.
Yes, I have 2 places to crash, and it's fantastic.
It's really hard for me, by the way. I have Turkish passport and we literally don't have any privileges. So I need to get visa for everywhere. So
Mm.
no for me.
I see, I see. Uh, what can we try is I'll try to share my remarkable input. Let's see how to do that. Screens, documents, no. Advanced. Okay. Do you see this, guys?
Yep.
Yeah.
Oh, super cool. Let me try writing something.
Yeah, perfect.
Okay. Okay. So yeah, let's open the session if we think everyone who has have his plan to come is here. So hi everyone, my name is Milica. I'm a DevRel engineer for ZK Verify. I'm also doing PhD in zero knowledge proofs. Today, we're gonna, go through the KZG commitment scheme. The thing with the example we're going to go through is that you need to have a pen and paper once again. We will not do the pairing on the elliptic curve that the original KZG has, but what we will do is we're going to use the power of algebra and see how that how the algebraic backbone is played with the KCG. So that's what we are going to show. Yeah, let's start with the trusted setup that we had last time. Let me just organize things here because I just arrived home, so I don't know where things are. I'm in fact nomad. In fact, one person approached me some time ago and said like, "How is it to be a nomad?" And I'm just like, "What do you mean?" He's like, "Oh, every week you're somewhere." I'm just like, "Oh yeah, okay, I hit that mark." So yeah, let's do case G. Everyone has a pen and paper? Yeah. That's perfect. Let me check if I can see also the chat here. If anyone asks something, uh, did not get burned, please. Yes. Okay, super cool. Super cool. I don't, if I'm sharing screen, I don't see comments. So if there is something, just like raise your hand and I'll see it in the bar with the camera. Okay, so we have for KCG, we're going to have a trusted setup. Trusted setup is done through something that we have shown in these classes, in these lectures of ours. It's called multi-party computation. So you remember when we were trying to calculate the average of our age, of the group age, we did MPC. So in fact, that's how we are having a setup in KZG as well. So we're going to start by calculating the setup. Okay, so it's cool that you see this well. Let me just, okay, it's gonna be black. That's it. Everyone sees it well. I'm not sure about the size. Okay,
Yeah, it looks good.
perfect. So what are we going to go through is setup, commitment, evaluation, verification, the 4 steps. Okay. Um, let's start with setup. Yes. So for setup, we need to form a certain group that and the generator. So it's going to look like this. Five, six. So this is our starting point where we can say that the G or the generator is 1 and the order of the group is 7. What does it mean, the order of the group? Okay, I can see the red dot now. Super cool. So the order here means that you can have only as many participants in this in this group as how big this order is. So if we have 7, the maximum number of the exact number of element will be 7. Right. Okay, let me just check one thing. Is everyone following?
Yep,
Do we
I
need
think board
something?
is a good idea. I love the writing, like,
Yeah, I was hoping I will use it in the previous ones, but I didn't expect that my trip in Milan would prolong. So then we had to do like actual pen on paper with my site. So here what we see is the G. The G is a multiplicative group. And yeah, so we're going to also define the field, which is the finite, we call it the finite field of prime order P. So what does that mean? The finite field means that the field can have as it needs to be of the order P, to say so. So it can have like 1, 2, 3, 4, 5 up until to P minus 1. Let's write that too. It's a finite. Finite field of. Okay. The group G. So I'm using all this so that, whoever is taking recording, they can also see it on the screen. Can you all read my writing?
yes.
Okay. Okay. If we have everything written down, now we have to calculate the global parameters, or where we see it as GP. And someone also is calling it the structured reference string, or SRS. So you will see both versions. Okay, so what we're going to do, we're going to do it like this: sample, random, tau. That's our secret, right? From FP field. Okay, so how big is our field? Our field is C. We have the G, right?
Are you writing right now? Oh, it
Oh,
just, I think
okay.
it's it's not connected right now.
Okay, sorry.
We see the
Okay.
tau.
Okay, yeah. Let me see where it stopped. Sample run it out from the P. Okay. All right. So let's see whether if something else is missed. Okay. So
Yeah.
we need the GP. All right. So these are the parameters, the global parameters that we have. And we're calculated in this way. We're gonna have H0 is G, H1 is tau times G, H2 is tau square times, right. And we can go to HD t to the power of d g if we are within the field of gd plus 1. This d that we have, it's a height of a polynomial. And in the end, we need to delete tau. So the MPC should delete tau after this step. So when we calculate h's, the global parameters, we should delete tau. We should not use it later. The fact that we're going to use tau for checking is just for the algebraic checking later in the lecture. Okay. So let's calculate GP for our example using this one, right? And saying that, okay, so first of all, we need to sample tau, right? Let's say that our tau is 5. So we're going to use this one. Okay. Yes. And we're going to use this top part. So GP is H0 is what? If we said that G here is 1, it will be 1, right? H1 will be tau times G. In our case, it will be 5. H2 will be tau to the power of 2 times G. And because we have modulus 7, it will end up as what? 25 modulus 7, it will end up as 4. So our global parameters are 1, 5, 4 respectively. Okay. And yeah, why do we have only 3 of them? Because the height of our polynomial that we have elected is this one. Let me just share it. Maybe I should have shared it before, because otherwise why would we stop at 3 elements, right? Okay, this is our polynomial minus 1. Only prover knows this polynomial, no one else. And the prover should prove to the verifier they actually know the polynomial, and they will do it by making evaluations of the polynomial when a verifier sends a value. We'll show it later. Okay, so now we have our, okay, yes, Hatun?
So if my polynomial would have been x cubed, I should continue till hash 3, right? Like it's not x squared, but if it would be like x3, x over 3, we should calculate one more hash, right? Like the order would have been 3 in this case.
Yes, this is why. Because with the polynomial, you will have, let's say that in your case, you would have, okay, I'm going to delete this, but let's write it. Let's say you would have like 3x to the power 3 plus maybe nothing combined with x2, or like 7x plus 14, let's say. So for you to be able to properly calculate this, you would need to have h for every of those, even if we have 0 here.
Okay, this is why we stop at 2 in our example. Thank you.
Yes, yes. So even if we had like, I mean, that polynomial wouldn't be used, but let's say that we only had like one height, we will one member, but it's then it's not a polynomial, right? But you know, even in that case, is like because you need to have a parameter for all the coefficients that are there.
Okay, thank you.
Okay. Mm-hmm. Delete this. Yes, vanished like that. Nice. Perfect. Okay, any questions regarding setup?
Can you explain again where do we get the g equals 1?
That
The
is something
beginning?
that the group that produces age values, they have elected that.
Got it.
Mm-hmm. Mm-hmm. So they're responsible for having GP. Like of course you would need to know the order later because you need to calculate the modulus, but you should know tau. So these secrets there, wherever you have tau and you need global parameters, that's what they calculate. So they need to know the height of the polynomial to be able to do that. Okay. Let me move. Yes. So nice. So much easier, right? Okay. Let's do the commitment. I hope we'll have enough time. Yes, we will. So what is commitment? That is our polynomial evaluated at secret tau. But because we do not know secret tau, we're using h values, the global parameters that the group sent, that the multi-party computation sent us. I don't like that we do not have nice brackets. Let's make it like this. Okay, so we said this is our polynomial, right? So let's write it from the lowest of the orders to the highest. So this is our f at x minus 1 plus 2x plus x to the power of 2. And we want to do to make a commitment so that we can send it to the prover. Is everyone following so far? Is everyone writing down? Super cool. Let me check just okay, nothing in the comment section. All right. So let's calculate commitment F. That is per formula F0 times H0 plus F1 times H1 plus F2 times H2. In our cases, we're looking here at the constants that are, let's say, like if it's like F0 that we see, that's the constant next to the x of power to the power of 0. So that's 1, and our constant is -1. So it says -1 times H0 that we had here is okay, it's still on the paper. It's here, so it's going to times 1 plus x to the power of 1 in our polynomial has a coefficient of 2, so it's 2 times h1 is here, it's 5 plus, with the same logic, we have 1 here times h2, which is 4. So that ends up in -1 plus 10, it's 13, modulus 7 is 6. This is what the prover calculates. Okay. For us to check it, we can do evaluation at secret t, secret tau, sorry. So this is not what the prover would calculate, but it's for us to confirm these two are equal and the equation stands. So we're going to do the evaluation of function in tau, and we said it's times g. It needs to fall into g field. So it's function of 5 times g, which is 1. It's modulus 7 because of this. What is it? It's because of modulus, I'll put it like the -1 plus 10 plus 25 and 7 is 6. So this is something what we do as an internal check. Okay. Now what we will do is do the evaluation. By the way, I'll ask all of you to try this at home with your own G's, your own U values from the verifier that's been sent to the prover with your own taus and everything combined. So and you know you can post it. So why not make your own toy KZG? So for the evaluation, we need to include the verifier too. So the verifier would say like, okay, let me send you something to see if you can do the evaluation for the commitment that you have. So here we would say, suppose the verifier said U is 4. That is chosen by the verifier. And we need to calculate the function function in U is V. We're going to use this later for finding zeros of the polynomial. U is a root of f, while f is calculated like this. X minus u divides f prime. At the same time, no, the prover nor the verifier should know tau. It should be deleted after the trusted setup, and we should only work with the global parameters. What we have here is also like how we're going to find the zeros. 3, that's q of x times x minus u because of zeros. Something. Okay, I'll mention the theorem later. Just not going to forget it. F and the point of u should be -1 if we are following. Okay, we still have the function here. -1 plus 2 times u plus u to the square, the power of 2. It should be -1 plus 8 plus 16. Okay, of course, modulus 7 should be 23 modulus 7, that should be 2. What does that mean? Because we said that, okay, that the end result, the result of the function at the point u should be v. That means our v is 2. Okay. So the f prime function that we're gonna have is f minus v, which is just shifted our function -3 plus 2x plus x to the square. Okay. Now, we need to find the quotient polynomial, which is not going to be sent by the prover or the verifier, but the evaluation of the quotient polynomial will be sent. And this is how, that's called witness. And the witness, this is the witness polynomial that we're going to see, or the quotient polynomial. Because we had this part, just here, for it to be much easier, q out of x is f of x minus v, 2 x minus u. This is the witness polynomial. If we do the calculations, it will be -3. Where is it? Plus 2x plus x to the power of 2 through x minus 4. And once we apply The modulus, we're going to add up with x plus 6. Okay, with this value is the value of witness polynomial. Looks like this. Because our quotient polynomial is x plus 6, we want to calculate the commitment. And that's what we call the evaluation, right? We'll calculate it by Q0 times H0 plus Q1 times H1 plus Q2 times H2. Oh, sorry. There's because we have the height is now 2, right? Because we have only x and there's no x to the power 2 or something with a higher order, we're going to have only 2 coefficients to be calculated. So in our case, Q0 is this one, x times H0 was 1 plus Q1 is 1 because the coefficient of x is 1 times H1 was 5. And we have to do modulus of 7. So here it's 11 modulus, not modulus. Modulus 7 is 4. This is commitment of Q is 4. This is the witness value. And only this is sent to the rover. Okay. Check if there are any questions so far. Okay, some people joined. Super cool. All right. So, we have seen that we're doing commitments, and those are the evaluations at the secret values. That's what commitments are. Also, the witness we calculated here, the witness value, that is per definition the object that convinces the verifier that the claimed evaluation that v is the result of a function with the value of u is consistent with the commitment q of x. I don't know if someone needs to. Do we need to go through the factor theorem of the algebra for dividing the polynomial or not? Please let me know.
I'm having hard time to understand like what is doing verifier prover and who is setting the u value. Like I'm sorry. I think I missed that part.
Okay. Let's put it on paper.
It's better now.
Yes. So how does the dynamic works? So we have global parameters, and the trusted setup is being done by a multi-party computation. Neither the prover or the verifier has any knowledge of that. They know only the global parameters. Then the prover says like, okay, I will tell you that I have a secret function that I will prove to you that I know it, and I'm going to do commitment. And the prover calculates the commitment, and the verifier is sending what's called like the challenges. Said like, okay, I'll send you some U, so we're gonna see if what you send back is falling within the zeros of the polynomial, because otherwise, if the prover does not know the evaluation, it will end up in fractions. And because it will not be like a round number what we have like 11 or something else, it will end up in fractions if we do not have a zero at that point of the polynomial. And because we're working, the KZG is meant to be within the elliptic curve, then we will not be able to convince the prover that we have that polynomial. So in other words, if the polynomial evaluates to 0 at some point, then x minus that point divides it exactly. Okay, that's what the fact theorem says. And if the v that we got, the root that is wrong, the division is going to fail. It would set this remainder, it will leave the remainder. And yeah, the verifier will catch it if the pairing check and that's being done on the elliptic curve is done. If v is correct, then division works perfectly, and q out of x is a proper polynomial.
Can I ask one more question? And this may be stupid.
No, there are no stupid questions.
Few years ago, I remember there was like KZG something in Ethereum, like I don't know, you need to go to their websites and type word and send them. Do you guys remember it? I don't know. Like I don't understand what is the reason, like why they used it. Like, for example, I believe Ethereum used this. I don't know, by the way. I just thought that, okay, I remembered something like KZG, but yeah. Yeah, that's in the comment session, Rasios writes, Semaphore did a KZG trust setup. Like, why do this?
So what I've seen, and probably it's I think it's the ceremony of the trusted setup. I think I even took part of it. So this is like the beginning, that everyone is calculating one part, and then everyone is generating the global parameters. So I think it's used for that one. That as many people that can join, so it's more deemed as more secure.
I see now.
Yeah, check. Oh, okay. So yeah, we need to do the verification as well. But yeah, before we go there, as yeah, did I forget something to share? Okay. Yeah, let's do the verification. Just wanted to check if I have something that, because we have a couple more minutes. Yeah, now we're going to do the verification part. We're going to pretend we're the verifier, right? Okay. How do we do verification? So in this example, because it's a toy KZG, like the real KZG is done with the elliptic curves, and points on elliptic curves, and the PQR are prim points. But here, because we do not know the pairings and the elliptic curve as a technology, we're going to show it as some more like practical example to see how does evaluation and algebraic check works, because that is the backbone of KZG. Once we go through example like this one, you'll be able to go and try understanding how it's working with pairings, etc. In the paper, I'll send it to you, the KZG paper. You will see that they're doing the multiplication. That is due to the cyclical groups that there are. We have additive cyclical groups, but there are also multiplicative cyclic groups. That means that what we're using here with the constants in front of every x, we are adding them, and that's how we do the commitments. But you will see that if you want to dive deeper, you will see that they're doing multiplications. Okay, the verification should be always so usually the weight of the calculation is on the prover and much less on the verifier. So the verifier should have easy task, and the prover should bear the weight of the calculations. So let's write that down. And be done with the Friday. Okay, so to do verification, I mean, like again, like the verifier know the prover, they do not know tau. We calculated, we checked the commitment using using tau, just for our own sake to see that the math is mathing, right? But yeah, like none of them, they know it. And in real world, verifier would use pairings to check, but for our case, the verification that we can check is, oh, why do I have this? Tau minus u times commitment of q should be commitment of f minus vg. Okay, let's check for numbers. So tau was 5, g was 1, u is what was u? U is 4. Let me check. Yes. U is 4, v is 2. And we got almost everything bar commitment of f. Commitment of q is here. Commitment of f. What is commitment of f? Does anyone wrote that down?
It was 6, I believe.
Okay. So the verification should match. So we have 5 minus 4 times commitment of q is 4. Should be the same as 6 minus time 2 times 1, and it ends up as checking. This is the algebraic check. And let me check if we have something else to mention, if we have skipped something. Yeah, so the only thing is that that the prover should not know, the verifier should not know tau, he will tau would be hidden in the real KZG scheme, but this is the toy KZG example. And the verifier will use pairings and elliptic curve instead to check the relation between the commitments. So that is all that we have for today. I would ask you to check it with your own examples, check it with your own small commitment scheme, with your own trusted setup, with your own modulus. Yeah, that's all, folks, for today.
Thank you. It was really cool to see the math behind. I was just so verifier define the U and everything. The prover is actually doing all the job. Verifier just check it is correct or not.
Yes.
Oh,
Yes.
okay. Okay, it's really cool. It was really cool.
Okay. Super cool, guys. Are there any questions? It is. All right, then we're going to wrap up the session, and yeah, that will be all.
Today I will try my own version, like to check
Sure
whether
thing.
I learn or not,
Sure thing.
and share it to the group. Thank you very much for additional session. Really, we take a lot of your time, and thank you very much.
Thank you for being there. See you soon.
See you soon.
Bye bye.
Bye bye.